Welcome to Why Bands Spread. So as a band travels down the column, it broadens and leaves the column with a standard deviation of sigma. And there are multiple mechanisms contributing to this broadening. Each mechanism has its own contribution, sigma sub I, to the overall standard deviation. Now the observed variance, which we're going to symbolize this way, is the sum of the variances of the contributing mechanisms. So the observed variance is equal to the variance from process 1 plus the variance from process 2 plus the variance from process 3 and so on. These should have a 2 and a 3 and so on. That's equal to the sum of our contributing variances. Now the solute can't be injected onto the column in an infinitesimally thin band, and thus the band has some finite width immediately upon injection. If the band is applied as a plug of width delta t, measured in units of time, then the contribution to the observed variance due to the injection is equal to delta t squared divided by 12. Note that an equivalent relation applies for broadening in a detector that requires delta t for the sample to pass through. Now, if there is dead space, which is a large volume in which material exiting the column can mix with material that previously exited or eluted from the column, then the band spreading will be quite large. Dead space and tube lengths should thus be minimized. The plate height h is proportional to the variance of the band, and the smaller the plate height, the smaller the variance of the band. So the Van Deemter equation relates the plate height to the linear flow rate u sub x and constants a, b, and c. So the Van Deemter equation is given here. We've got h, which is the plate height, is approximately equal to a plus b over u sub x plus c times u sub x. And note that I've given some labels here. A is from multiple paths. This second term here is from longitudinal diffusion, and the third term is from the equilibration time. And so note that our Van Deemter equation states that there are band broadening mechanisms that are proportional to the flow rate. Those are C here. There are some mechanisms that are inversely proportional to the flow rate. Those are the B terms there. And there are some mechanisms that are independent of the flow rate. Those are in the A there. And so you can see over here, we've got plate height as a function of flow rate. And so we have some mechanisms that are independent of the flow rate. Those are that A term. We have some mechanisms that are proportional to the flow rate. These are the C term. And then we have some mechanisms that are inversely proportional to the flow rate. So they start out very high and they end up very low. And that's that B term. When we add these all together, we get this blue curve. And so there's going to be some minimum in that curve, so some minimum plate height at a moderate flow rate. So in packed columns, all three of these terms, A, B, and C, contribute to band broadening. Whereas in open tubular columns, there is only a single path, and thus that A term is 0. And therefore the bandwidth decreases and the resolution increases. In capillary electrophoresis, both A and C are 0. And thus we have even better resolution. So suppose that we could inject a thin disk of solute in the middle of the column, here, instead of at one end. The band would broaden over time as molecules diffuse from the region of high concentration to regions of lower concentration over on each side. And this is called longitudinal diffusion. This is that B over Ux term in the Van Deemter equation. And that is, the faster the flow, the less time that band spends in the column, and thus the less broadening from diffusion will occur. Now, recall that the variance from diffusion is given here, where D sub m here is the diffusion coefficient of our solute in the mobile phase, T is the time, L is the length of the column, and U sub x is the linear flow rate of our mobile phase. And note that the time required for the mobile phase to travel the length of the column is L divided by U sub x. So the plate height due to longitudinal diffusion is then given here, where we have HD, so the height due to diffusion. The plate height due to diffusion is equal to the variance divided by L, which is equal to 2 times dm over U sub x, which is equal to B over U sub x. So that B is 2 times dm. Now the third term in the Van Deemter equation, that CUX term, arises from the finite time required by the solute to equilibrate between the stationary and mobile phases. So while some solute is in the stationary phase and thus is not moving, some solute is in the mobile phase and does continue moving. And this means that the band is spread. So at some time, if we have equilibrium, we've got some in the mobile phase and some solute in our stationary phase. And you can see that we've got some bandwidth here. But as the mobile phase travels to the right, that means that now the solute that was in the stationary phase hasn't moved, because the stationary phase is stationary after all. But the mobile phase has now carried some of that solute farther down the column. And that means that unless equilibrium occurs instantaneously, then this sort of back end is now in front of the back end of the stationary phase solute. And thus, we're spreading the band over time. So the plate height due to finite equilibration time, which is also called the mass transfer term, is H mass transfer is equal to C times UX, which is C sub S plus C sub M times U sub X, where Cs is the rate of mass transfer through the stationary phase, and Cm is the rate of mass transfer through the mobile phase. Now for gas chromatography in an open tubular column, Cs is given by this equation, and Cm is given by this equation, where K is the retention factor, D is the thickness of the stationary phase, D sub S is the diffusion coefficient of the solute in the stationary phase, R is the column radius, and D sub M is the diffusion coefficient of the solute in the mobile phase. Now, decreasing the stationary phase thickness D decreases the plate height because less time is required to equilibrate a thinner stationary phase with the mobile phase. And decreasing the column radius R decreases the plate height because less time is required for the solute to diffuse from the center of the column out to the stationary phase that coats the walls. And increasing the temperature increases the molecular speeds of our solutes, and thus it decreases the time required for diffusion. So now let's look at that first term in the Van Deemter equation. That's that A term, and that used to be called the eddy diffusion term, and it arises from multiple effects which are poorly understood at this time. One of these effects arises from multiple flow paths available to our solute. So let's examine 3 different solute molecules that take different paths through our packed column. So our first solute particle here is traveling this path. Our second particle is going to travel that middle path, and our third particle is going to travel a much wilder path. So molecule 1 is taking a very direct path. It's not deviating much radially along the column, and thus it's going to be eluted first. Molecule 2 takes a somewhat more meandering path, and thus it's going to be eluted later. So molecule 1 comes out before molecule 2 does. But molecule 3 takes an even more wildly meandering path, and thus it's going to be eluted even later. So simply by having different paths available to our solutes that initially started out next to each other there, they end up being eluted at drastically different times, and that means that our peak has spread. So again, note that our 3 molecules entered the column at the same time, but they've now exited the column at different times because they've traveled different distances through the column. And that means that the solute band has broadened. In gas chromatography, we can use either packed columns or open tubular columns. Open tubular columns provide a higher resolution and sensitivity to small analyte quantities. But open tubular columns have a small sample capacity and are thus suitable only for analytical separations. That is, they're unsuitable for preparative separations used in industrial applications where you need a large volume or mass of your solute. The solid particles in a packed column resist the flow of the mobile phase, and thus the linear flow rate can't be very fast. And the relative lack of such resistance in an open tubular column allows for a much faster flow rate, and this allows us to use a similar pressure and flow rate, but a much longer column, which can be up to about 100 times longer for the open tubular column compared to the packed column. And if the plate height is the same between the two columns, then there are 100 times as many theoretical plates with the open tubular column, and that means that the resolution is 10 times greater with the open tubular column compared to the packed column. So recall that resolution scales with the square root of n, the number of theoretical plates that we have. Now in reality, the plate height of an open tubular column is smaller than that for an equivalent packed column. There is only one path through the open tubular column, so that a term in the Van Diepter equation is 0. To obtain the best performance from our open tubular column, then, the radius of that column must be small, and the stationary phase must be as thin as possible to allow for rapid equilibration between the stationary phase and the mobile phase. And a Gaussian band shape occurs only if the partition coefficient k is independent of the solute concentration. So remember that k is equal to Cs over Cm, where Cs is the concentration in the stationary phase and Cm is the concentration in the mobile phase. But in reality, k changes as the solute concentration changes, and that means that band shapes are asymmetric. So a graph of Cs versus Cm is called an isotherm. So we've got a few isotherms shown over here. The ideal isotherm is this blue line in the center. This one is where k increases as we increase Cm, and this one is where k decreases as we increase Cm. So that upper isotherm, this one here, is arising from an overloaded column in which too much solute has been injected. That is, as the solute concentration increases, the solute becomes more soluble in the stationary phase. And this occurs because the concentration of solute in the stationary phase is so high that the stationary phase begins to resemble the solute. And because like dissolves like, the solute will then be more soluble in itself. And so as we put more solute into our stationary phase, the solute gets even more soluble in that stationary phase. That lower isotherm here is arising when small quantities of solute are retained more strongly than are large quantities of solute. That is, some sites bind our solute more strongly than other sites do. For example, silica surfaces have hydroxyl groups that can form hydrogen bonds with polar solutes, leading to a significant tailing of peaks. And silanization reduces this tailing by changing the hydroxyl groups that we have on the end into nonpolar trimethylsilyl groups. The glass and silica columns used for gas and liquid chromatography can also be silanized to reduce the interaction of the solute with active sites on the column walls. So that was why bands spread.